Welcome everyone. In this video, we're going to take a look at how we can trace the creation and really the use of objects from C++ code using Ghidra. So we're going to have a couple of example programs here that we'll go through. Our focus really will be on identifying how they're created, being able to understand the structure, the amount of memory that's actually needed, and then we'll talk a little bit about virtual functions and how that changes the makeup of our objects. If you want to get the sample code, you'll be able to follow the link in the description of the video and either check that out from my GitHub or just download those files. To compile any of these programs, I'm just going to provide the source so you can certainly play around with them. I am just using the latest version of Visual Studio, the Community Edition, and actually I'm just going to use the developer command prompt. So once you install Visual Studio, if you look for the developer command prompt in your system, you can open that up. That will give you CL in your path. That's the Visual Studio compiler, and all you have to do from there is navigate to the location of your C++ files, and then you can compile the programs. Assuming that there are no syntax errors, then that will generate the .executable, the .exe for you. And I went ahead already and compiled all of our programs here, so I won't have to take time to do that now throughout the rest of the video. Also, since we're going to be using Ghidra, I've already created a demo project here that contains all three of those programs. So that's also something that you can do once you've got those compiled if you want to follow along. Now, to get started then, we'll take a look at our first basic C++ program, and this isn't meant to be a lesson on the best way to program in C++. Again, I wanted something that was relatively simple and straightforward that would allow us to reverse it and see what that looks like after it's gone through the process of being compiled. Because there's a lot of things that if you've never looked at, in this case, an object that was created, compiled, and then you've reversed it, you've decompiled it, disassembled it. A lot of things can be kind of surprising. Now, the definition of this object starts with the class. It's ex1, example1. There are a number of member variables, var1, var2, var3. var2 and var3 are public because they fall in beyond this public label. var1 is internal, and that means that we have access to var2 and var3 if we want through an instantiation of that object. Not really all that big of a deal here. I just created a few so that we could talk a little bit more about how much memory is actually needed for these objects. And then when we talk about virtual functions, how the memory needed changes a little bit. In addition to those variables, those members, we have the constructor, and then we have a member function. So the constructor is going to do some just really trivial things, and I really wanted it to be obvious once we are reversing this so we can see that we're in the constructor. So I have this basically this print statement that says in constructor, and we're also going to talk about how, and as we're tracing the memory that was allocated for this object, we're going to see it being used here as we set this var1 equal to 1. We'll actually also see these variables as well. Now, if we look at the main function, this is also relatively straightforward. There is one local variable a. We'll initialize that to 0, and we'll assign that the return value of this function here, which just returns the value of var1. We also then have a pointer that will point to our object. So this is where we instantiate or create that object. Now, if we just take a moment here and think about memory, local variables will typically take up space on the stack. So we have a local variable a, it's an integer, that's 4 bytes. So 4 bytes on the stack. We have a pointer. This will be a 32-bit program, so pointers are 4 bytes wide. So this will also take up 4 bytes on the stack. So we really, based off of what we've defined here, only need 8 bytes. If we think about this object now, right, this 4 bytes will be a pointer to the memory that is allocated for this object. That will be in the heap. How much memory do we need for the object? Well, we have 3 variables. Those are integers, each 4 bytes. So 4, 8, 12 bytes for this object. And we don't need any additional space for the constructor or this member function. The compiler will generate these functions, and the way that these that we'll be able to tell that they're part of this object is through the use of this pointer. the pointer for the memory allocated for our object will be moved into the ECX register before both of these function calls. And we'll see that here when we get into the analysis in Ghidra. So 8 bytes on the stack, 12 bytes on the heap. So that's what our object looks like. So let's go ahead and open this up in the code browser. Now I've already got this window open. I guess what we can actually do is we can go back to the project view. If you're not familiar, one way to open up these is to just double click. You can also take whatever program you want to analyze and drag it to the code browser, which is the dragon icon. Now, the first time you analyze these, Ghidra will tell you, hey, I have not actually done the analysis, the disassembly, so it's going to prompt you to do that. You can tell it yes, because if you don't, then you won't have any code to analyze. You'll just have all the bytes. For these sample programs, it's safe to just pick the default, go ahead and analyze. And now this will take just a couple minutes here as it goes through and does the disassembly, controls, or explores the flow of the program. Once that's done, then we have, the first real task we have to identify or accomplish is to get to main. So one thing that you'll notice that since we defined all of our code essentially in main, the things that we care about analyzing or that it's using our object in main, when we compile this, the compiler will add a lot of additional code. And so the entry point of our program is not necessarily main. It's compiler-generated code that eventually will call main. So if we're not careful, we can spend a lot of time analyzing compiler-generated code, which can get a bit painful and certainly not be the type of code that we want to analyze. So now that this is done, if we expand functions, scroll down until we find the entry, this is the entry point. So there's a call and a jump. And you can see that all of this code here in the listing view is also what you see over here in the decompiler. What we're looking for is one of the easiest ways to do this, at least with the code generated from Microsoft through Visual Studio, is 3 pushes before a call. And those 3 pushes represent argc, argv, and environment p, which are generally the 3 arguments to main, as you can see here in the sample program. Now, it's not as obvious to look at that in the decompiler, at least not initially. And so what you might end up doing is in the listing view, just scrolling down here until you find the 3 pushes in the call. You'll notice that this is generally 3/5 or so of the way down in this function. And so you really kind of pick up the pattern, and it's easier to identify once you've observed this a few times to just find the function here in the decompiler window. But if not, if all else fails, the 3 pushes in the call, you can always find that in listing view. Here you can see we've got the same function identified, and now we have identified main. So in main, there's going to be probably a couple of things that immediately jump out as deviations from that original sample program. One of the first is that in our prologue, so the little bit of code that is setting up the stack frame for this function, we have a sub ESP 14 hex. So it's subtracting 14 hex from ESP. We're getting a lot more space on the stack than the 8 bytes that we discussed. Again, this is something that the compiler decided to do as it was generating this code. And you'll at least see why there's so much more space on the stack here in a moment. The other thing, and it's more apparent here if you look at the decompiler window, is we have an if-else. And we certainly don't have an if-else in our original program, right, in main. There is no conditional logic here. And so what's happening, and we'll get into this in more details in just a moment, but essentially what's happening is the compiler is decided to test if the allocation for our object returned a null pointer, a 0 value, or if we got an allocation, a memory allocation, so a non-zero address. And that's really what this branch is doing. So it may be a bit unexpected, and certainly it's unexpected if you are new to this type of reverse engineering. So let's start at the beginning here, and let's just kind of bounce back and forth between the listing and the decompiler and figure out what's going on. So after the prologue, these first 3 instructions, we can see that we're moving 0 into local 14. If you recall from our original sample program, that is our local variable A. So it's always helpful if you have an understanding, or if you have the source code, great, line things up. If you don't, which oftentimes if you're reversing you don't, then you might want to give it at least a more meaningful name. Now we've just begun analyzing this program. If we didn't have the source, we probably wouldn't know much about it. But since we have the source, we can hit the L key. That'll bring up the select action. And we can use the first option there, and we can just call this var a or int a or something that lines up better with our source. That way, as we see this used later on in the program, it's much more clear what variable we're working with. We don't have to go back and try to remember. Now, after that, we have a push and a call. So this call is taking an argument of C hex, or 12. Well, that's the same number of bytes that we determine is the size of our object. What isn't quite clear is what this function call is, and this is our call to new. Now, if we start drilling into this function, we're getting into compiler-generated code, and this can, again, take you down a kind of a rabbit hole that you likely don't want to go down. So with some other tools like IDA Pro, IDA has really good signatures, and IDA would identify this as a call to new. Ghidra isn't quite there yet, but we can still contextually analyze this and come to the same conclusion. So we've already got a big clue, and that we're pushing the value of 12 of C hex onto the stack, which is the size of our object. If you look at how the return value is used here, right? So let's just assume that this is returning a value because EAX is being moved into this local variable, the stack space. Then we can now follow that return value and get even more insight into what it possibly could be. So we think it might be pointer to our object. And at this point, I would say it's probably not a bad idea to relabel that label as a pointer to the object. And sometimes I put little question marks behind it just because that's like a note to myself that I'm not 100% confident in that. So let's say it is, though. So we now move that into this local variable, and we then compare that to a value of 0. So memory allocation routine, it potentially can return a null pointer if it was unsuccessful in allocating the memory, and that's what we're comparing. So the comparison takes the value in that local variable, that stack space, and it's dereferencing it using those brackets, and it compares it to 0 with the compare instruction. JZ is a conditional jump if 0 flag. So if the values were equal, we're going to take this jump. So if the value returned was 0, then we would jump to this location right here. All this does is it moves 0 or null into local 10, and then we get on with the rest of the function here. So that's the end of our else branch. If it's not 0, that means we got an address, our allocation was successful, and what we're doing now is we're moving that pointer into ECX, and we're calling this function. So this function then is actually our constructor call, and we can determine, or we can start to suspect, that we're dealing with not only the constructor call because of the way that this is being called immediately after the allocation of memory for the object, but also because a pointer to that memory was moved into ECX. We can now double click on that function, and if you scroll down just a little bit, you'll see, as I mentioned earlier, why I put some of these strings in the constructor, so that it's very obvious and clear that we have identified the constructor. So that's really the pattern that we can follow here. Now, if we go back to the beginning of this function, right, and again, we can look at both the listing and the decompiler view, you'll notice that the calling convention here that Ghidra has identified as fast call. And this is a Microsoft convention that favors moving arguments. Instead of pushing them on the stack, it moves the first 2 arguments into registers and then pushes the rest onto the stack. So we saw that we moved the pointer to our object into ECX and called the function. That's all we did. That's really was our only argument for this function. So it's identified the use of the ECX register as param1. So now in the beginning of our constructor, we have typical Prolog stuff, push EBP, move EBP ESP. We then have a push param1. Now you'll see this from time to time, and that instead of doing a sub ESP4, the compiler decided just to do a push. So that's all this is. It's not saving param1 necessarily on the stack. It's just clearing the 4 bytes of stack space for use in this function. Now from there, param1, or the pointer to our object, and again, we can go ahead and hit L, select edit label, and we can call this pointer to our object. that gets moved into local 8, so onto our local variable. And then that gets moved into EAX. And then EAX gets dereferenced +4, and 2 gets moved into that location. Right? So this local 8 is the pointer to our object. If you recall, when we looked at the structure here, I said that there would be 12 bytes, right? 4 bytes, 4 bytes, 4 bytes. That means that the first 4 bytes, so the very beginning of the allocation, will be var1. The next 4 bytes in, so +4, will be var2, and we'll initialize that with a value of 2. And then at an offset of +8, to get the last 4 bytes, we'll give it a value of 3. And that's what's happening now inside of the constructor, is that we have moved the pointer to our memory, our object, into EAX, and we're now dereferencing from the base, from the base of that allocation +4, and then moving that value of 2. Okay, the pattern continues, and that we now are moving our local 8, so that local variable that contains the pointer to our object, back into a register. From there, we take an offset of +8 from the base of our allocation or our object exists, and we move a value of 3 into that location. Right? So offset of 0 is the base of the object, var1. Offset of +4 is var2. And then an offset of +8 is then var3. So those are the 12 bytes that would account for really the makeup of the object. The next thing that happens here is local 8 gets moved into EDX, a register. We now dereference EDX. There's no offset needed because this is the first 4 bytes of the object. We move 1. So these instructions, which you can see over here, are accounting for that initial value that is assigned to those variables. And then we get into really the custom code that was defined in the constructor itself. After that, we have some function calls for the print statement, the couts and the endels that just prints the in the constructor. Before finally, we're going to move the pointer for our object back into EAX, and then the function will return. So the pointer to our object is ready there in EAX, which is the conventional register for returning a value in. Okay, if we go back to main then, what will happen after that function call is EAX, pointer to our object, is moved into local 10, and now we jump to location 401104, right, which is after the else branch. So that's after our if-else. This is one of the reasons that you're seeing all of the additional stack space that was needed here, is because the compiler has decided to really shuffle the pointer for our object around into different local variables. I can't say 100% why, it's just how it's doing it. Now from there, let's go back and look at our sample program again. What we're doing is we're calling var1 and then assigning these values to those 2 variables for our object. And we'll see then that local 10 gets moved into EAX, EAX gets moved into local 8 gets moved into ECX, and then we have a function call here. Now in this case, this is not the correct label for this function. And so sometimes you just have to recognize when those are incorrect or not. It's not always easy. But one thing that really stands out here is that the pointer for our object that we've now traced from its original creation, its original allocation, is moved into ECX. So it's this pointer. It means that now inside of this function call, it can reference this pointer, the value in ECX, to have access to the memory for that object. So if we go into this function, and let's just bounce back here real quick, because all this function is going to do is it's going to return the value of var1. And we'll see that here, that we are moving this pointer into local 8. Local 8's moved into EAX. We dereference the first 4 bytes, the memory, to get the value, move that into EAX, and now that's in the register for the return. If we go back to main, EAX is now moved into var A, which is what we expect from our original program. A gets assigned the value from that function's return value, and we can continue on to the next calls. Now, I guess there are no other additional calls. We're now just accessing var2 and var3, which we've really already seen. right? The pointer to our object gets moved into ECX. We dereference that at an offset of 4 to get the second variable. We do the same thing, dereferencing at an offset of +8 to get the third variable. And then we have the call to delete before the end of the function. So that's really what's going on with our object and some of the changes that the compiler has made from our original source. Now, if we look at our second example, the only thing that I'm really going to change here is I'm going to simplify the object a bit, get rid of some of those variables, those local members, and add 2 virtual functions. The idea behind a virtual function is that it allows for polymorphic behavior in our classes. So if we are not going to ever allow other classes to extend or inherit this, then virtual functions are really pointless. The idea behind them is that now another class could inherit or extend this class, and then it could redefine these functions. So it could have a new version of int sum with 2 integer arguments, and it could redefine the logic. Why the virtual function then comes into play is that when these programs are compiled, the compiler has to make sure that the right version is called. Is it the base class or is it the inheriting class? So that's where the virtual function comes into play. Now, when we look at the size of this class, this object that's going to be created, we know we're going to have 4 bytes for this variable. We're also going to have 4 bytes for a pointer to the virtual function table. So that will be the first 4 bytes. This will be the second. So the size of this object should be 8 bytes. Let's go ahead and let's load up our second project. So I'm going to open that. I think I forgot to analyze it, so we'll have to just take a second here as that analyzes, and then we will go ahead, navigate to main, and analyze it. In terms of the code in main, instantiate the object. We call the 2 virtual functions just so you can see how those look, because since we've defined these as virtual, we're going to have to use the virtual function table in order to call them, and then we'll delete the object. So we're going to really just focus on the constructor. Even though it's not defined here, it's still the constructor is still going to be called in order to populate the virtual function table. So we're going to focus on that, and then how those virtual functions are called. So it looks like our analysis is complete. From the symbol tree, we go to functions, go to entry, scroll down about here, and here is main. Now you'll notice again that things are they look very similar to what we previously saw. Right? The stack is a little bit larger than what we were expecting, but that's because of all the shuffling of the pointer for our object. And we have the if-else, which is again very similar logic here. It's testing to see if the call to new returned a null pointer, a null value, and if it did, it just assigns a null value to this local variable, and then it continues on. So it isn't going to prevent the code from crashing, right? But good programming practices would dictate that you actually are testing to make sure that your memory was allocated for your object. It's just essentially avoiding the call to the constructor. Now, when we look at the else branch, so we're looking at what happens when we do get memory allocation, you'll notice there are a couple of additional statements. We're dereferencing PUVAR1. PUVAR1 is the pointer to our object, right? And there's our argument, 8, so that's the size of the object. So we know that's how our object's being allocated. We dereference that, so we're dereferencing the first 4 bytes, and we're moving in a value of 0. We're then treating this like an array. This is how the compiler decided to approach it. We're accessing the second element, right? So if the first 4 bytes is the first element, then the next 4 bytes would be the second element. And we're also assigning that a value of 0. And you'll see this here in the disassembly, and that we move into dereference the ECX EAX. If we need to figure out what EAX is, though, you can actually hit Command, and that will highlight that register for us. So a couple instructions up, we see that we've XORed EAX with EAX. Anytime you do that, that zeroes out that register. So XORing something with itself will provide a result in 0. Local C is moved into ECX. All right, that's our local C then is the return value from our call to new. So that's our pointer to our object. And from there, we're moving EAX into dereferenced ECX, right? So that's how the actual assembly for moving 0 into ECX. So what it's doing is it's zeroing out the memory that was just allocated for our object. It's assuming then that the allocation, which typically is the case, that the memory that was allocated could still have residual content in it. And so this is just making sure that that's actually zeroed out before it's used. Now, if we go into the constructor, right? So this function here, you'll notice that this one's a little bit more straightforward because we don't have the print statements, we don't have the initialization of those variables, those members. But what we do have now is the virtual function table. Now, you'll notice that in the listing here, it looks a bit different than in the decompiler view. In the decompiler view, what we're seeing is param1, right? So ECX is this pointer that contains a pointer to our object, memory allocated for object, that's param1. That's being dereferenced as indicated by that asterisk, and it's being assigned this address. What you see here in the listing view is that our param1 is moved into this local variable, much like you saw with the last constructor. That gets then moved into EAX, and EAX is dereferenced, and EX2::VF table is moved in. This is the address then to our virtual function table. And if we double click on that, what we'll find is that is a pointer then to an array of functions. And those functions then are the functions that are the virtual functions defined for our class, our object. We had 2 virtual functions, which means that in this vtable, we have 2 elements, 2 virtual function addresses that are defined. So if we go back to our original constructor then, hit that one more time, right? We're dereferencing the first 4 bytes in order to populate it with the pointer to our virtual function. After that, we don't have any additional logic in our constructor. And recall, we didn't define a constructor here. So it's being called like the constructor was previously, but we don't have any additional logic for the class. So it moves our pointer to our object into EAX and returns. Now, how is the virtual function table used? Well, in order to see that, we need to go back to main. And what we're looking at now are these 2 function calls. This is our call to delete. So our 2 function calls, because these are virtual function calls. So from our constructor, EAX is moved into local 10. Local 10 is now a pointer to our object. That's moved into EDX. EDX is moved into local 8. Again, we see all that kind of shuffling going around. For our first function call, though, we're passing 2 arguments. It's going to just provide the sum of those 2 arguments. So push 2, push 1, and then we move local 8, pointer to our object, into EAX. We dereference, move that into EDX, and EDX is then dereferenced into EAX, and then we call EAX. Before that, we move local 8 into ECX. So there's 2 things that happened here. We've populated this pointer so that in this function we have a pointer to the object. So if it needs to access anything from the object itself, it can do that. But we also walked the virtual function table. So let's go through that again, right? Pointer to our object is moved into EAX. We dereference that into EDX. So the first 4 bytes was the pointer to the array of virtual functions. We then dereference that in order to get the first element, move that into EAX, and then we call. So these are indirect calls. And what we can't see right now is what function are we actually calling. Now, we could do runtime analysis or debugging. We could set a breakpoint here, and then we could see the address that's in EAX. But if we can trace the constructor call as we did, we can also navigate there statically. Okay, and let's do that in a minute, but let's look at the second call because you'll see the slight difference here. Remember, the first call was to the first virtual function, the second call was to the second virtual function, and you'll see the same pattern here repeat except for one difference. So local 8, pointer to our object, moved into ECX, ECX is dereferenced into EDX, we populate this pointer, but before now we're ready to make the call, we dereference EDX plus an offset of 4, moving that into EAX, and then we call EAX. Right? So our virtual function table is an array of function pointers. 32-bit program, so each one of those elements will be 4 bytes wide. And so if we want to get the second function, then we have to dereference at an offset of +4, which is what we're seeing here. Now, as you already saw, if we want to go and actually investigate those functions, then we just simply need to navigate to the virtual function table. And now we can double click on either one of those functions, and we can see exactly what's going on inside of those virtual functions. Okay, the last thing then we'll look at is just the last call here. Let me refresh my memory. Yeah, it's the... Nope, we've already looked at them. So the last call is just the call to delete. So that's really it for that program. I'm going to go ahead and load the last program. This has a combination of virtual and non-virtual. And then let's take a look at that here in the source code. So very similar to the previous, there's only one addition. That's this method here, void print hello, not virtual. So that means that in terms of the makeup of this object, we're going to have 4 bytes for the virtual function pointer, pointing to the virtual function table. We'll have 4 bytes for this local variable, so it's an 8-byte object. And this function then here, the only way we'll be able to recognize it as a member function, a function for this object, is because of the use of this pointer, the pointer to our object being moved into ECX. Okay, inside of main, we'll allocate the object, we'll call the virtual functions and then the non-virtual function, and then that'll be it. So let's see how that looks. Okay, first things first, we got to get to main. Here we go. Okay, so this looks almost identical. We have the same check for the null pointer after the allocation. We have the size of our object being 8 bytes. The memory is being zeroed out before it's being used in the function. We can, or in the constructor, we can navigate into the constructor. We'll see there is our vtable. Now this label here is what was left in the program from compiling it. It wasn't obfuscated or removed or stripped out. Oftentimes you'll see, particularly with malware authors, anyone trying to add some additional obfuscation, that they'll remove this value. This comes from RTTI information, runtime type information. And so with each pointer to a virtual function table, so let's go back here. Right, here's our constructor call. All of the same logic is being applied here. We're dereferencing the first 4 bytes of the object to move this pointer to the vtable into that first 4 bytes. But if you look at the 4 bytes preceding that, then you have a pointer to this RTTI information. So this is information that can be walked in order to find and oftentimes recover the original class name and things. And then that's where part of this information is coming in order to actually identify the original name of this class. So that's how Ghidra was able to do that. And you can explore this. This is a pointer to a series of different structures. It's kind of documented online. You have to do a little bit of digging, and maybe we'll cover that in a later video. In terms of this vtable, though, we have 2 addresses because we have 2 functions that we defined as virtual, the first one and the second one. And so again, very, very similar to the previous example. Okay, after our constructor, we return the pointer to the object, just like we saw previous examples. And now we're ready to make those virtual function calls. So we can take a look down below, indirect calls, right? So the code is then going to navigate the appropriate offset in the virtual function table to position that function into the register to make the call, as we're seeing with this code, also populating the ECX register with the this pointer. And this then is the last call for the object. And you'll see that we can identify that because it's moving into ECX, a pointer to the object. Otherwise, it's not altogether that obvious that is what that this particular function necessarily has any relation to the object itself. You can navigate into the function and you can see how it's using ECX if you have any doubts. And in this case, again, we can see that it's populating that into a local variable before. And it doesn't really use it here in this example since there's no other functions being called or we're not referencing this local variable. Okay, so that's really the kind of the basics of getting started with reverse engineering objects and seeing how they're identifying when they're being allocated and being able to trace their use and identifying the use of virtual functions. In some additional videos, then some things we can look at are when we have multiple inheritance. So when we have objects that are actually inheriting from others and overriding those virtual functions, and then what happens when we have a class that inherits multiple classes that each have their own virtual functions. And so I'll post some additional videos here, and we'll explore this topic in a little bit more depth. So hope you enjoyed, and talk to you soon. Thanks.